hopefully you guys have taken a breather and we are ready for our final block of talks. Next up is Georgi Spasov, a developer of Quanterall, who is going to present Noise, the encryption protocol of the peers.
So, hello everyone. With this presentation, I hope to explain in the next 20 to 30 minutes what an encryption protocol is, how Noise does it, and why do we use it for the communication for the peers. So first of all, what is Noise? Noise is a framework that helps in creating secure channel protocols, such as TLS or SSH, which are actually widely popular, where usually you would have two parties, let's say a client side and a server side, which are going to be on the same time online, which can authenticate each other or exchange few messages so that they create a key agreement for encrypting messages between themselves. So one of the main questions would be, why would you use Noise? And we have two main points here. First of all, secure channel protocols don't actually do much. They should be quite simple. Their main idea is to exchange a few messages and establish a secure shared secret key so that maybe Alice and Bob can continue communicating through a secure channel without someone else getting this information or tampering it. As well, existing ones that I have mentioned, maybe TLS or SSH, are usually quite complex and hard to extend for new uses or new cryptography that comes because with years to come, old cryptography sometimes gets old, new algorithms come, and new crypto comes to the world where sometimes we need to extend it and add it to our secure channel protocols to implement it. So where do we actually use Noise in the blockchain? And simple is that we use it for the encryption communication between the nodes, or as we call them, the peers. So before I continue with the secure channel protocol, I'll just go and give you a bit of crypto background. So first of all, I'm going to look into Authentication Key Exchange, or as we call them, AKEs. So an AKE is a sequence of messages which is exchanged by two parties, let's say Alice and Bob, to authenticate each other and establish a shared secret key for further secret communication between themselves. The properties that an AKE has, first of all, we have forward secrecy. What forward secrecy means is if we have Alice and Bob, for example, they would have, let's say they want to create a secret channel protocol, communication today. So they will create a session key, two keys, which are going to be a public and private key, which are going to be session keys. And they will establish, using the secure channel, they will establish communication with these session keys, and they will encrypt some messages, talk to each other today. The next day, they will create another session key and establish a new shared communication. So if a hacker comes and breaks their keys from yesterday and reads their messages, he cannot use the same method to do to the keys used in the next day because they have used new keys. So this actually gives Alice and Bob the possibility to have a new encryption each time they communicate, so that a hacker cannot just get one of the keys and decrypt all of the messages that they have for the future. Of course, AKEs can have mutual authentication, which means that Alice authenticates to Bob and Bob authenticates to Alice, or one-way authentication. So if, let's say, an Alice is a client side and a Bob is a server side, maybe Alice needs to authenticate to the server being Bob. Of course, we have the property of pre-knowledge of identities. So maybe Alice has a pre-knowledge of the public key of Bob. Or we have something called identity hiding, which is before Alice and Bob authenticate to each other, they'll establish a secured key, and using this secured key, they'll going to authenticate to each other, so without another person knowing who are they exactly. And we have a lot of different crypto use, a lot of different signature, DH, and different types of encryption. DH is actually Diffie-Hellman operation, which is quite commonly widely used in AKEs. So now I would like to give you an example of how a Diffie-Hellman actually works. So if we have here Alice and Bob, which want to create a secure channel of communication between themselves, and Eve is going to represent the public area. So when Bob and Alice communicate to each other, the public area is going to maybe get all the information that Bob is sending to Alice or Alice is sending to Bob. So when we're starting, Alice has a private key and Bob creates his private key. In the public area, we have this G, which is a shared arbitrary number, and all of the keys we're going to represent with colors, and you see in a moment why. So what Alice and Bob does is they take this shared arbitrary number and they put it to the power of their private key. And here I have done, for example, addition, but it's actually doing to the power of their private key. And they'll end up with their public key. So Alice goes G to the power of A, and Bob's goes G to the power of B. So they'll end up with some color for themselves. Next, Alice is going to send her public key to Bob, and Bob respectively sends his public key to Alice. So now Alice has the public key of Bob, and Bob has the public key of Alice. Next thing that they do is take. So for Alice, she's going to take the public key of Bob and put it to the power of her private key. So she'll end up with the key GBA. Bob is going to do the exact same thing. So he gets the public key of Alice, put it to the power of his private key, and actually they'll end up with the same key. Here we have GBA, and here we have GAB, but it's actually the same key. And from this point forward, they can continue to encrypt and decrypt messages with this symmetric key, because now they have one key for encryption and decryption. In a public area, Eve has a shared arbitrary number, the public key of Alice and the public key of Bob, but whatever she does, she cannot calculate this shared secret key. Basically, she could do it, but it would take so much time and computational power that she wouldn't bother to do it, unless for some reason she gets the private key of Bob or the private key of Alice. And this is what we call a discrete lock problem. But there is a problem with this approach, and the problem is the key size. So for example, if we take a security of 128 bits, for RSA and DSA, we have a key size of more than 3,000 bits for this security. If we use, for example, elliptic curve, we have 12 times less size of the key. And in some cases, this may not be that much of a problem, but when we're dealing with a lot of keys, and in the blockchain community, we are actually dealing with a lot of keys, this size matters. So elliptic curves come to the rescue, and actually we have elliptic curve Diffie-Hellman operation. And this is what I'm going to explain right now. So here we have basic elliptic curve, and what it basically is we have an x-axis, the y-axis, and we have a curve on this axis. Depending on the type of the curve, it's going to look in a different way. This is just some generic type of curve. So on this curve, again, we have this shared arbitrary number G, which everybody knows. It's in the public area. What we make here is this dot operation, which what it is we put a tangent on the point G on this curve, and we intersect with another point on the curve. We flip this point on the other side of the x-axis, and we get 2G, which is this dot operation. Then we do this again. We put a tangent on the point 2G. We intersect in a point on the curve. We flip this point on the x-axis, and we get 3G, and so on and so forth. And we continue this almost close to infinity. So in this case, let's say we have this point n dot g. So this would be n times doing the dot operation. So the key n is going to be our private key, and the public key is going to be the number which is going to represent the result of doing this n dot g operation. Doing this operation n dot g times, it's actually quite fast. The problem is it's really, really difficult if you have this final number n dot g to having this public arbitrary number g to find n. It's so hard that usually what you would do is do g, find 2g, find 3g, find 4g, 6g, and so forth until you find this number. So, and of course, here we are talking about a number which is, let's say, 128 bits, so quite a large number. So again, we have the discrete log problem, which we had in the normal Diffie-Hellman. But in this case, we use quite less size of the key. So let's go back to secure channel protocols. So in a secure channel protocol, I'm just going to explain in a simple way what it actually does and what it has as components. We basically have two main components of the secure channel protocol. We have this transport phase and the handshake phase. The transport phase is quite simple. This is the phase where when we have already created our shared secret key, we just encrypt our data and send it back and forth between, let's say, Alice and Bob. The handshake phase is where it gets a little bit interesting because this is the place where we authenticate and establish the shared secret keys that Alice and Bob are going to use. So in the section of handshake, we have one of the components is, of course, the Authentication Key Exchange, or the AKE, that I described earlier. So this AKE is going to execute our secure channel implementation depending on what types of protocols that we use in here. One of the other parts is the negotiation. And the negotiation is where Alice and Bob negotiate between different types of options that they could use for different types of AKEs. So because we have a lot of different cryptos, we have a lot of different DH operations, we can have a lot of different types of AKEs and transport phases depending on what options we have. So for example, in big security channel protocols, we have a lot of different AKEs, a lot of different cryptos. So we have a lot of different possibilities that we could use here. The problem is that this brings a lot of complexity, and if we want to implement something new, we have to have in mind all of these AKEs and transport phases that we already have so that we can put something new on top of this. What Noise does, it gets the AKE and transport phase and put it on these specific protocols. And these protocols, let's say, we have them put on the side, and we have them more done in the design time of the protocol. And in the runtime, we only, let's say, choose to use only these three AKE and transport phase protocols. So in this way, we have a simpler and easier to implement secure channel protocol. So if we zoom in into one of these noise protocols, what we have inside is some abstract AKE, which is going to instantiate our public key crypto, so the different type of DH that we could use, and the symmetric key crypto, so when we end up with this shared secret key, what type of cryptography we're going to use to encrypt the data. And if we put it to the notion of the framework, we have this negotiation layer when Alice and Bob are going to choose which type of these, let's say, three protocols that we have implemented they're going to use. So they select a protocol, they execute it, and maybe in the end they will have to encode some of the data. So there is some encoding layer if we need it. But for the reason to use these protocols, what Noise does, it gives them really simple names. So actually this is a name that is used as a protocol in noise. And these names are actually going to represent what is the type of the protocol. And we have 4 aspects of the protocol that we're going to use. So first we have the pattern name, and there is actually a way of having these protocol names in the noise, but I'm not going to talk much about this. And in the next slides, I'm going to show how actually the noise language goes into doing those abstract AKEs. Next, we have what DH name we're going to use to establish our shared secret key. In this case, we use the DH25519. Then we have the cipher name, which is going to be used once we get this shared secret key. So when we get this shared secret key, we are going to encrypt and decrypt the messages with AES GCM. And we have a hash name if we are going to use the encoding layer. So there are not much of a patterns that a noise implements because it wants to keep it simple. So if we, let's say, have Alice and Bob are going to have a static key, which is going to be used for authentication, and they're going to have an ephemeral key, which is going to be used to establish this session key for forward secrecy. And the patterns are resolved around all of the intersection of these keys that they could be. And we have actually only 4 of them. And reading from left to right, we have this SSDH, we have the SE, which is going to authenticate Alice, we have the EASDH, which is going to authenticate Bob, and EE, which is going to be used for forward secrecy. Now I'm going to show a few examples of the language that eNoise uses. And to have it more understandable, the right pointing arrow is going to represent the initiator, the left is going to represent the responder, and the 3 dots is going to represent prior knowledge, which we're going to see in the next slide. So in this case, we have an unauthenticated key exchange. So Alice is sending her ephemeral key to Bob, and Bob is sending his ephemeral key doing an EEDH. So they establish a shared secret key without authenticating each other. In this case, Alice has a prior knowledge of Bob's static key, so she sends her ephemeral key and does an ESDH, which is actually going to authenticate Bob. So this is this part over here. At this point, we have a mutual authentication. So we have prior knowledge of. So Alice has a prior knowledge of Bob's public key, public static key, and Alice has a prior knowledge, and Bob has a private prior knowledge to the static key of Alice. So this is what represents the prior knowledge. And then what it's done is we have Alice sending her ephemeral key and doing an ES, which is going to authenticate Bob again. And then she's going to do an SS, which is going to authenticate herself to Bob. And this final one that I show here is actually the pattern that we use actually in the blockchain right now. And what this is let's say Alice is going to represent node 1, and Bob is going to represent node 2. So node 1 has a prior knowledge of the public key of node 2, and then he's going to send his ephemeral key and do an ES. So he's going to authenticate node 2. Then node 2 is going to send his ephemeral key, do an EEDH for forward secrecy, and then node 1 is going to send his static key and authenticate himself to node 2. So how do we implement the noise? And here I have created just a simple diagram, which is going to explain in a simple way how this is done. So we have, again, node 1 and node 2. Node 1 is going to try to create a TCP connection to node 2. If this TCP connection is successful, we're going to receive a socket from which we can continue our communication. Then we're going to start doing our eNoise handshake. But before that, we actually have this prologue data, which is actually going to hold the version of the blockchain that it is at the moment, and then Genesis hash. So before the part of the handshake is done, we're going to see if this prologue data is the same on node 1 as in node 2. So if the version and the Genesis hash is the same. If it's not, the handshake is not going to happen because node 2 maybe is on a fork, and we don't want to actually establish a communication with him. If the prologue is the same, so the version in Genesis hash is the same on node 1 as in node 2, the handshake is going to be established, and then if everything goes well, node 2 is going to accept all of the options that node 1 has. So right now we have hard-coded the pattern that we use for the handshake. So if everything goes well, node 2 is going to accept this protocol, and they'll establish a secure channel protocol, a communication. And from there on, we're going to add, each of them are going to add the other to their pre-list, and then they can continue communicate further privately. So let's say if they're going to sync to each other, sending blocks, all of these blocks are going to be encrypted with this shared secret key that they have established using noise. So if you want to go further into the code, you can see our implementation on GitHub/Aeternity/Elixir node. And if you want to read more about noise, go to their website, because I have just scratched the surface. If you have any further questions or in some regards of how we have implemented this, you can find me on my email, and I'm open for questions. Thank you.
I would like to know how you review, or how is your review process of components like this?
So how do we review on which?
The implementation of the noise protocol, for example. Who does your review? Do you do it internally? Do you talk to the noise community? How is the review process?
The noise implementation itself, so the implementation of the whole noise protocol is actually done by the Eternity team. And inside our code base, we are using this implementation of the noise protocol to establish the communication inside. And the pattern that is used, we use quite new and established Diffie-Hellman, which was, let me go back, which is this DH. And for the cipher, we use Chachapoly, I think, 15. So all of this is established. So like, for example, Bitcoin is using the CSCP-256 as an DH, but there were some questions about whether if it's quite secure and if it has some loopholes. And I think right now the best one there is this 255.19. So we already have the data of what protocol name we're going to use. We're using this implementation of noise that Eternity has made, and we just have it basically integrated in our project.
Thank you.
Do we have any other questions? If not, then thank you.